Welcome and thank you for joining us for today's webinar, Smarter Sunlight, the Optimization of LED Solar Simulators, brought to you by Intersolar and Energy Storage North America and sponsored by Innovations in Optics, Inc. We have a few housekeeping notes to go over before we get started. If you need any technical assistance, we first recommend refreshing your browser. If you continue to have technical questions or issues using the On24 platform, please use the Q&A box and I will respond as soon as I can. There will be no call-in number for today's session. To connect, you need to have access to either a computer, tablet, or cell phone audio. Everyone has been automatically muted. If you happen to get disconnected, you can log on again using the instructions provided in your webinar confirmation email. If you continue to have trouble, please email isnainfo@divcom.com and we'll respond as soon as we can. For your convenience, everything in the webinar console is fully customizable, so you can move things around, resize the window, and even turn on captions for this event. At the bottom of your console, you'll also find a resources box where you can download the slides as well as any additional content for today's presentation. And again, you can ask questions at any time by submitting it through the Q&A box. We'll leave some time at the end of the session to answer as many questions as time allows. And finally, this webinar will be recorded and you'll receive a thank you email with the on-demand materials within 2 business days. And with that out of the way, I would like to introduce our speaker for today. We'll be hearing from Karen Allardyce. Karen is a business development and application engineer at Innovations in Optics, a distinguished leader with decades of experience in ultra-bright, solid-state illuminators known for their exceptional uniformity and stability. She holds both a bachelor's and a master's degree with thesis in optical engineering from the University of Rochester's prestigious Institute of Optics, along with the postgraduate studies in the physical life and life sciences at Harvard and UCLA. Karen brings over 20 years of experience in the optics industry, encompassing management, R&D, and proof of principle experiments. She has worked for major corporations, including General Motors Research Labs and Northrop Grumman, TRW, where she contributed multiple technical publications and conference presentations in high-energy lasers and nonlinear optics. A GM Research Scholar National Winner in Optics and TRW Graduate Fellow. Karen has received numerous commendations for technical excellence and customer engagement. Integrating customer success, optical engineering, and market development in solar simulation and photonic illumination, she drives the adoption of IOI's high-power, spectrally tunable LED systems for research and industrial markets worldwide. At this time, I would like to welcome our speaker and hand the webinar over to Karen.
Thank you, Jovi, for that lovely introduction. Hello, everyone. Thank you for joining us from near and far. Good morning, afternoon, or evening. We appreciate your time. So, as Jovi mentioned, the subject of the webinar is smarter LED solar simulators, and I will add not just smarter, but classier. I'm speaking to you on behalf of our solar division, actually, of Innovations in Optics. We have decades of experience in LED technology, and we've sold thousands of OEM solar simulators over the years and benchtop versions. In fact, I may have had the pleasure of meeting you most recently at PVSec in Spain, Bilbao, Spain. If not, perhaps you can visit our booth at SPIA Photonics West in San Francisco in January. And also we will be exhibiting at Intersolar San Diego in February. So I hope to see you there. So welcome. And to begin, as Jovi mentioned, my name is Karen Allardyce. My background is in optical engineering. And of course, I'd like to give a shout out to University of Rochester. Our CEO and CMO are also alums. I have been at IOI for 6 wonderful years, where I now work in business development and applications engineering. So let me give you a brief overview of what we will cover. I'll give you a little history on innovations in optics, talk about the focus of the webinar and specifically applications, a bit of general solar simulator technology, and definitions that apply to all solar simulators, along with reference spectra overview. And then we'll dive into LED solar simulators specifically, regarding key design characterizations and considerations, 2 or 3 systems to review for extended spectrum, bifacial, and PV characterization, and also comparisons of solar simulators, and Q&A session at the end. So who are we and where are we? We have been LED innovators for many years. We have over 80 patents with many more in progress, actually. We are close to Boston, easy access from Logan Airport. Come visit us. We have a large facility that includes a clean room, research and development labs, and expertise in all of the engineering disciplines, optomechanical, thermal, electrical, as well as system level experience, which is helpful when we're designing larger systems, and we need to incorporate all of those disciplines. They're interrelated. We manufacture also in high volume and for copy exact applications. So not only does IOI have a solar division, you'll notice to the right here a plethora of products. We also play in other markets such as medical, semi, industrial, machine vision, multispectral and hyperspectral illumination. You see many of our product offerings here, including our main subject, the LED solar simulator to the right, the tall instrument. So solar simulation supports numerous applications, right, across multiple markets. I'll present an overview of solar simulation, but the focus today will be on the attributes and design considerations, interpretation of performance that might be handy and useful to you, and challenges associated with LED solar simulators. So we all know photovoltaics is a growing market, and it's ever evolving, so it tends to push all of this technology forward. However, we are at no loss for other applications needing engineered sun, from materials degradation studies on plastics, coatings, and textiles, to photodynamic therapy for cancer and macular degeneration, and testing sensors, and of course, sunscreen research and development to protect us from the very sun we seek to emulate. So let's talk about what types of solar simulators are out there in the world. There are many. Traditional ones include lamp-based designs. For example, the Xenon-arc lamp. The fastest growing for cutting edge research has been the LED-based. They offer a lot of flexibility and special features that we'll discuss in a few minutes. There's also a metal halide lamp, specifically for UV aging, flash solar simulators. They can be pulsed or pulsed xenon or LED. And then multi-source hybrid simulators. They extend the spectrum, bit of calibration challenges associated with those though, and high flux concentrated systems for many, many suns. Solar simulator designs naturally evolve alongside PV industry trends as manufacturers push toward the higher module power and, of course, lower cost per watt. The industry has migrated steadily to larger silicon wafer formats, and that's what you see here in this pictorial. The largest wafers now exceed 217 millimeters. So this drives the need for larger, more uniform illumination fields in both research and development and manufacturing environments. IOI has aligned its portfolio with this evolution. Our LumiSuns cover illumination fields from 50 millimeters on out to 220 millimeters square, with our future roadmap to include 450 by 450 to support the next gen PV technologies and large area manufacturing, keeping our customers at the forefront of high efficiency solar innovation. So this chart gives a high level comparison of 4 major solar simulator technologies used in PV in particular today. Each technology has its strengths, but they differ significantly in spectral quality, stability, lifetime, and other parameters. LED simulators lead the way with its multi-channel tunability. There's no warm-up time associated with them, and they are the preferred choice for advanced PV mostly. Xenon lamps were the historical standard, but they struggle with spectral mismatch, of course, lamp aging and limited lifetime, which translates to larger cost. Metal halide systems offer peak irradiance, but lower quality and short lifetime. Flash systems are essential for module level production testing and very large area devices. They do deliver extremely high irradiance in a short pulse, which makes them good for concentrated PV and multi-junction cells, but not quite as accurate for detailed research and development work. So each solar simulator has a niche, but for advanced PV characterization and precise measurements, LED systems deliver unmatched accuracy, stability, and lifetime. So how does one define sun? Because there are different reference spectra depending upon where you are in the world, on Earth or in space. And not every solar simulator has all of those capabilities. The solar spectrum varies according to time, position, atmospheric thickness, clouds. AM0, shown by this orange curve, represents space, and AM1.5G, shown by the blue curve, is the standard for solar cell testing, and it's also known as the terrestrial reference spectra. It includes diffuse and direct sunlight on Earth, but clearly one sun for AM0 differs from AM1.5G. There's reduced UV content below 350 nanometers for AM1.5G due to ozone absorption and scattering. In addition, you'll see several bands labeled there, but water, oxygen, and carbon dioxide are also responsible for significant absorption, and it significantly alters the AM1.5G curve. This translates to solar simulator designs for AM0, though, that have more wavelengths at higher power to ensure a comparable low spectral deviation. So what should you look for when selecting a solar simulator, and how do you compare them? There are standard metrics. The IEC defines class rating based on 3 key performance metrics. You see them listed in order here: spectral match, spectral non-uniformity, and temporal stability. But for modern PV technologies, the IEC class alone is no longer enough. Very important are spectral coverage and spectral deviation in particular. When you compare solar simulators, start with the IEC class rating. These define the baseline performance. But for advanced PV and highly accurate measurement, especially perovskite and tandem devices, you need to also look beyond IEC classification. So those were the metrics for all solar simulators. Now let's get specific. Why would you want an LED solar simulator versus lamps? Well, there are many reasons. They're a lower cost in the long run. They can test many different cell technologies, and their qualities are right up there in terms of spatial non-uniformity and temporal stability. They're safer. You don't have to risk explosive bulb failure. They operate at lower temperatures, in fact. They're more efficient, and they have fast control as well. You can individually tune the wavelength. That's important for many applications. And you can do so electronically with no shutter, fewer optics, no igniters. They're fast to operate, no warm up, no cool down like lamp systems. And they're compact and easy to integrate. Also, not to forget, they're friendly to the environment, no mercury or ozone emission. And so eventually mercury will be removed from all environmental operating systems. So now that you realize you should have an LED solar simulator, let's talk about the design considerations for such simulators. Because designing an LED solar simulator requires thinking from the top down. Let's start with precision. This is precision you need to achieve. Then you build the power and engineering foundations to support it, and ultimately deliver results that matter to you, to the user. This is how we approach our design. And it's a good approach for you as well. If you're looking to buy a solar simulator, what should you look for in both a company and in the simulator itself? So it begins with understanding the test conditions you must simulate. Do you want AM0 or AM 1.5G? So space or terrestrial. The number of suns that you need, the wavelength range, and the size. So achieving high accuracy depends upon the performance metrics we discussed, as well as engineering across multiple disciplines, optical, electrical, mechanical design. Next is power. This is the engineering backbone, really, of the system. It includes lifetime, stability, and thermal management, which is very important in terms of keeping junction temperature low, making long lifetime. System control matters as well. So being able to create custom spectra depends upon high quality electronics. Finally, at the base, we have results. So what the user, you actually experiences, reliable performance, intuitive setup, easy calibration, and long-term cost effectiveness. Good engineering at the precision and power levels translates into lower operating costs for you and longer lifetime than lamp-based systems. So high-performance solar simulators involve a lot of steps. They don't happen just by accident. They're built from the top down, resulting in a reliable, accurate, user-friendly system. So when designing LED solar simulators, it's important to have deep experience in solid-state technology to produce the optimum results. Because take, for example, different LED dye types. They have varying heights, sizes, and emission. This affects manufacturability, uniformity, and long-term reliability as well. You'll notice the image here shows an array, a 3x3 array of 9 LEDs with different formats. So there's reds, there's whites, there's blue, a little bit patriotic. Variations in the dye height or placement can impact uniformity if they're not handled correctly. The number of dye used in each wavelength needs to account for differences in the radiant output. In addition, dye sourcing is critical. A well-designed simulator depends on LED dye that are consistent and readily available. The wider the wavelength range, the more challenging the design, and higher class systems with precision and accuracy do tend to use more LEDs. And so this does present a system challenge. The good news is that there are many LEDs that exist out there. So I'm just showing you a graphical example of some LED dye that are available, and of course their relative performance. If you look at the graph on the left, I think that goes from about 350 on up to a little over 1,000. The graph on the right is all the way up to 2,500 near IR. But you can see the general trend as you go from lower wavelengths on up to the higher near IR wavelengths. There is a decrease in the power offerings and a few smaller LED powers in between. So that's important to know when you're designing a system, and it requires expertise to deal with mapping that out in an actual solar simulator so you obtain the right reference spectrum. Let's talk about a few parameters that should be important to you. Let's discuss spectral coverage and spectral match, because these terms are often confused, but they actually measure completely different things. Spectral coverage describes which wavelengths a simulator can produce, and this is critical for advanced technologies which absorb all the way from UV out into the near IR. Spectral match, on the other hand, is one of the IEC Class metrics. It tells you how closely the irradiance in each of 6 IEC defined spectral bands matches the reference. In fact, a simulator can pass Class A spectral match or Class A plus while still having major gaps or spikes between LEDs as shown in the graph. So let's take a simple analogy, the piano. SPC tells you whether the piano has all 88 keys, and we hope that it does. Spectral match tells you whether the pianist hits those keys accurately according to the score. That would be good. And in solar simulators, you need both. A simulator might have excellent spectral match in the IEC bins, but poor coverage. So it misses large portions of the actual solar spectrum. That's exactly what we're showing in this plot. The black curve is a solar simulator that meets Class A, but it has poor spectral coverage in the ultraviolet visible and near IR in some of the valleys there, indicated by the orange circles and ellipses. So just like a piano that can't play half the notes or one that plays the wrong melody, a solar simulator with poor SPC will give you the wrong data, even if it claims to be Class A. And that's not easy on the ears or on your data. So spectral match is not everything. In fact, it's very easy to meet. What you really want to look at and to understand is spectral deviation. And you want low spectral deviation. As defined, it measures the sum of the errors between the solar simulator and the reference spectrum. You can see on the curves, the red represents the reference spectrum. And it's more of a point by point, it's a very detailed type of metric. So an LED simulator must reproduce not just the average irradiance in each bin, but the correct spectral shape near material band edges for good precision. For example, modern PV, tandems, perovskites, and multi-junction require accurate shape, that is low spectral deviation, not just good spectral match, not just good class. So the graph on the left illustrates an LED solar simulator with good spectral match as Class A, but poor spectral coverage and high spectral deviation. The graph on the right shows a LumiSun with sufficient numbers of LEDs and an optimum design. Spectral deviation is low and industry leading. The LED spectrum matches the reference, and it will accurately simulate all ranges needed for example, perovskite, cadmium telluride, and silicon. The spectral deviation shown there is actually less than 9% for the range 400 to 1100 nanometers, less than 12% for a broader range. And so this represents a simulator that will be accurate for you. As the second class descriptor, uniformity is also an important metric. It's actually classified as non-uniformity. This is an example of what is achievable with an optimized optical design. Imaging systems have inherently less sensitivity to changes in working distance. Moving off nominal, as you see here in the graph, by 10 millimeters decreases uniformity by less than 3%. There is an intensity fall off, but less than 10% over 10 millimeters. Systems with longer working distance and larger illumination field have even less sensitivity. The uniformity plot on the right shows a LumiSun with better than a Class A plus non-uniformity. So it's excellent with a low non-uniformity less than 0.8%. So that's also for all of the wavelengths and for individual wavelengths as well. So you'll note also that the IEC standard requires the calculation with a 5x5 grid. We actually show and use in our system an 8x8 grid. That's more strict, and we think it's a better indicator of performance. So actually the reported non-uniformity would actually appear better with the 5x5 grid. But the goal is to minimize sensitivity to image location off of nominal. But imaging systems give you that kind of flexibility. The third part of class designation is temporal stability. And this depends heavily on good thermal management. Both flux and wavelength shift as a function of temperature and drive current. So temperature stabilization is required to prevent spectral shift, particularly near band edges, such as 800 nanometers for perovskite or 855 nanometers for cadmium telluride and 1107 nanometers for silicon. So you have to be very careful what LEDs you choose around those regions, and also to control them very specifically to minimize temporal instability. At IOI, we control to 0.1 degrees C to ensure that the spectral output remains constant and captures behavior around those band edges. So this shows you specifically what happens if you do not control it. Sensitivity to thermal fluctuations varies with LED type, but they are sensitive to both changes in drive current and also changes in temperature. UV LED dye tend to shift to shorter wavelengths under higher drive current and board temperature. Infrared LED tend to shift longer in wavelength. So I'm showing an example of a near IR dye of 840 nanometers. It shows a shift of almost 20 nanometers as temperature increases. This is significant. You'll see that LEDs emit in discrete narrow spectral bandwidths with finite full width half max. Each three of those curves there show you the broadening of the curve of the LED profile. But spectral shifts can move that irradiance out of a wavelength region and severely compromise the accuracy of an LED solar simulator. For example, as the red curve indicates, cadmium telluride absorbs efficiently up to about 855 nanometers, but it falls off sharply after that. If you have an LED that shifts outside that band edge, it may no longer produce the true AM 1.5G irradiance in the 800 to 900 region. This will dramatically affect the accuracy of the solar simulator, and it's something that you absolutely need to control for. For example, the graph on the left, the bar chart shows you the total integrated converted energy drops on the order of 50% when this kind of thing happens. So the LED spectrum, in short, should match within the entire bin, not just on the average. So how do we control to maximize temporal stability? There are different methods: thermoelectric cooling, liquid cooling, free convection, forced convection. Passive cooling is not enough to ensure temporal stability. Multi-channel LED systems in particular benefit dramatically from TEC stabilization because spectral mixing will remain constant. So compared to lamp-based systems, the best LED systems often achieve Class A+, which means it's less than 0.25%, according to the specification. And I'm also showing you a quick look at what is inside LumiSun 50, in case you've only seen the outside, which is better than Class A+. So in the diagram, or in the picture, you can see there's a heat sink coupled with thermoelectric cooling plate, the general optics assembly. So that's what's inside, so that you get the high precision and accuracy that you see on the outside in the illumination field. So in addition to good thermal design, the solar simulator should be easily aligned for working distance, and it should be easily adjustable vertically and rotatable to redirect the illumination field and give you more flexibility. As mentioned, imaging systems like the LumiSuns are more forgiving in non-uniformity and intensity fall off than non-imaging, but they still require alignment to accommodate sample heights. Many systems employ laser pointer converging dots as a visual aid, or other mechanical means are available as well. I'm showing a graph here on the bottom left, and that's in particular for the LumiSun 220, so that's a bigger model. And you'll see the variation in intensity and uniformity is minimal across a distance of plus or minus 10 millimeters. In fact, non-uniformity change is less than 0.05% over that range. Variation in intensity is less than 3% over plus or minus 10 millimeters. And that's something that's achievable with imaging systems. And finally, precise electronic control of the LEDs is critical. Drive conditions vary for different LED die. And so this is accounted for in the electronic design, firmware and software. LED solar simulators are capable of spectral tunability, which is a terrific feature. Not only can you individually control the LED wavelengths, but you should be able to adjust the number of suns for your specific test requirements. Class requirements are defined at 1 sun, but it's also nice to have extra margin. As you see in the GUI clips on the right, LumiSuns can hit the 1.2 suns mark. And in addition, there is sufficient resolution to scale down to 0.1 suns. If your application requires flash testing, this is accomplished through high-speed drivers with, fortunately, no need for shutters. Shutters are typical of lamp-based systems, and they add complication. It's not something you have to worry about for LED solar simulators. So ideally, you want a system that is stable over a long time, tens of thousands of hours. LED-based systems offer this over lamps. If there's ever a concern about recalibration, though, there are options. You can send it back to the supplier or calibrate on site with a reference standard from the supplier. How often you calibrate is very much system dependent. For example, AM0 with its inherently higher irradiance may need calibration before an AM 1.5G terrestrial system. So let's talk about user-friendly operation and flexibility, because we certainly all want that. LED solar simulators offer significant flexibility in adjusting both the number of suns and in controlling spectral output. This is an example of GUI designed to allow changes in the spectrum. The orange curve that you see there is the AM 1.5G reference spectrum. And the white curve shows the LED spectrum from a LumiSun. Output can be set for each channel by entering a percentage of the wavelength desired. So you see there are 3 by, I don't know, 1, 2, 3, 4, 5, 6, 7, about 21 channels shown there. There are more. And the percent can be set by the user. In addition, you can save the setting and come back to it later. There's also standard communication that most simulators have between RS-485 and using RSB communication. Yeah, USB, excuse me. With LED solar simulators, it's easy for users to focus on different regions of the spectrum. For example, if you are interested in red and blue spectrum for PV characterization, this is set individually through percent of 1 sun, as shown in the GUI here and on the previous slide. Different wavelengths penetrate to different depths. Blue or UV, shallow absorption near the front surface. Red has deep absorption near the rear regions. So by tuning, you can selectively study which layer of the device is performing poorly. Also, for example, researchers could check current matching in perovskite and silicon tandem cells, blue for the perovskite, red for the silicon. And specifically on this graph, you can see where I have turned on the blue and turned on the red. The orange is the reference spectrum. So you can do that for any sets of wavelengths. Additional display features also should include diagnostics, right? You want to keep track of the health of your solar simulator. We monitor temperature of the LED, the PCB, the heat sink, all of those to ensure good health of the solar simulator. So now here's a little something that will be useful as you go forward, understanding what you're looking at in terms of irradiance or any other display on a GUI or readings, because understanding what is reported is important, but not always obvious. So I'll touch on a couple of the nuances. The definition of 1 sun is over a broad range. It's from 280 to 4,000 nanometers. However, since there's little contribution in the far infrared and lower UV, most simulators operate over the range consistent with PV technology, or where most of the contribution from the sun would be. Thus, 1 sun setting at 100% with all LED dye on will only report the total irradiance over that restricted range. So even though one sun is defined as 1000.4 watts per meter squared, the solar simulator will show a portion of that to be about 759 watts per meter squared for a smaller wavelength region. The irradiance displayed is consistent with the definition, but necessarily and properly lower than one sun. In addition, LED solar simulator designs use multiple LEDs for one wavelength. Setting it to one peak wavelength, which you can do, will report a lower irradiance at that wavelength than what may actually be present in the spectrum, the reference spectrum, or the LED output spectrum. As you can see, there's overlap of LED dye. You're seeing 3 LED dye in that lower right-hand graph. Turning on only one in the middle will not include its sister reds on either side, and they contribute to the total spectrum shown by the dashed lines. So just a couple of things so you understand how to interpret what you're seeing on a given solar simulator's output. So for complete characterization of a solar cell, solar simulators are often used with PV characterization modules. Integrated systems offer ease of setup and measurement, for example, pairing our LumiProbe and LumiSun, though the LumiProbe actually is compatible with LabVIEW, and we can use it, or you can use it with other solar simulators as well. LumiProbe in particular exceeds IEC and ASTM standards. It's also capable of tracking the temperature of the PV cell and providing correction. But the important point here is that PV characterization gives a clearer understanding of the physical, electrical, and material properties of a PV device. The test parameters that you see listed help detect manufacturing defects, aging, and degradation, compare material technologies, and ensure compliance, and assess overall conversion efficiency at every wavelength. It helps answer how much usable electrical power does this device generate. For example, IV and EQE are essential for research and development as an aid to optimizing new materials and in manufacturing to ensure quality control, improve yield, or fine-tune deposition thickness. Also, you can predict field performance, simulate output under different climates, and there are many, bifacial responses, temperature effects. So shown here is a typical IB graph. It's a GUI clip from a PV characterization module. This is from IOI's LumiProbe. And you can see various parameters such as fill factor. In fact, high fill factor means less deviation from ideal behavior. LumiProbe tests for more factors than required. And customers can choose point density and other features along with data storage. IOI can also give you direct customer support since LumiProbe is designed specifically for solar testing compared to other more general systems. So I will touch briefly on a few different configurations and types of solar simulators, beginning with bifacial. As you see, the picture on the right shows you sunlight not only hitting a solar cell from the front surface, but also it has the capability of being illuminated on the rear side, functioning bifacially. So this technology makes use of light from all directions and is often combined with tandem or multi-junction cells as well to achieve greater efficiency. So when you're testing these types of cells or the type of technology, you need a solar simulator that can illuminate both the front and rear sides. And they do differ in their spectrum and, of course, their illumination needs. There's a different spectrum and intensity for each of the two solar simulators, but with LED solar simulator systems, that's easily achievable. Their tunability in the spectrum and sufficient resolution allow that to happen. And LED solar simulators can accommodate studies with different ground albedo. basically a backside albedo emulator, if you will. So here's an example of an albedo emulation. LED solar simulators with low spectral deviation and high coverage can produce both the high intensity and the spectral content of various albedos shown in the graph. With their individually controlled wavelengths, programmability, stability, and variable suns output, they're an excellent choice for this type of research because of their flexibility. There are numerous applications that benefit from this capability. For example, as a tracker tilts, the rear sight illumination varies significantly. Also, you'll see in the chart the blue LED spectrum compared to the red reference spectrum, and all of the curves for various albedo, and they differ pretty significantly, but you can adjust your solar simulator output to mimic this. So the dynamic albedo contribution influences the total energy yield. It could be sand, grass, snow, rooftops, or soil. And so it is important to characterize this. And LED solar simulators are excellent for this type of application in research. So with the latest developments in LED dye, LED solar simulators can now extend down to 300 nanometers. But there are design considerations, of course. Material selection is important. The bar graph on the right illustrates the relative output for various LED from UV to near IR, even down as far in the UV as 325 nanometers. There are the contributions to the solar spectrum in the near IR, it's less, which is good in a way since near IR LED dye emit less power, and so in any event, more dye can be used to meet the spectral requirements out in that region as well. The third specialized system I'll mention today is for concentrated photovoltaics. Solar simulators exist well beyond one sun to facilitate this research. I broke them into 4 categories. There's the low multi-sun range, anywhere from 2 to 5 suns. You can test for minor thermal stress, varying linearity and responsivity for EQE lab sensors, radiometers, LED feedback diodes. And then we have the 5 to 10 sun range, sort of a medium range for accelerated testing AR coatings, adhesives, characterizing early saturation in perovskite and tandem cells, and for automotive and aerospace studies, perhaps sensor heating, material expansion, optics fogging. There is a high range, 10 to 20 suns. That's good for concentrated photovoltaic cell characterization, optics under high flux. You can pre-test samples to detect microcracks before submitting them to an environmental chamber, reveal solder fatigue, evaluate cell hotspot behavior, and other degradation mechanisms. And then you have the ultra high range, as I've called it, anywhere from 20 to 50 suns. You can use this for high irradiance stress tests for aerospace flight modules, stress test materials intended for use in spacecraft, and autonomous vehicles. Also, any kind of testing that's required for harsh illumination environments to predict what's happened and whether your substance or your material is durable under those conditions. And as an example, here's the LumiSun 55 high, and that goes up to 20 suns. We can get you to 20 in an area of 55 by 55 millimeters. So to summarize, what should you look for in your LED solar simulator? Well, whatever your requirements, broad spectral coverage and low spectral deviation should certainly be highly coveted for accurate measurements. Don't be fooled just by spectral match. High class AAA plus is optimum and speaks to temporal instability, high uniformity, and spectral match. But equally important is long lifetime inherent to an LED solar simulator, but only fully realized when paired with proper thermal management, as we discussed. At IOI, our goal is to ensure that you have the best possible performance across a broad range of simulator types. And we'll talk about the LumiSum family as shown here, as a broad range of selection. Each LED solar simulator has a purpose depending upon your requirements: high suns, panel or wafer testing, large or small illumination fields, and research and development. All of these can be coupled with a PV characterization model, for example, the LumiProbe shown there, for a complete system. And just to highlight a couple of the LumiSuns that you see there, on the left is the high brightness. Coming soon is our 450 millimeter large area for PV panels system. LumiSun 220, you've probably heard about that. If you haven't, it's an excellent model for testing wafers. And the LumiSun 50 is a benchtop research and development type of model, with another version coming soon with ultraviolet. There are many reasons to choose LED solar simulators. They are the future of solar simulation. And also you should be choosy and looking for a supplier. The best instruments require expertise with solid state illumination. And that's why we're here. We're IOI Solar, and that's Innovations in Optics. We stand by our technology and products, and we would be happy to help you. So please visit our website, look for this page here, and discover why IOI. So this concludes the slide presentation, but please feel free to contact me and IOI. We have a global distributor network as well to whom you can reach out. As I mentioned, you can stop by our exhibits at Photonics West. We will be there, booth number, I think it's 343. And that's in January. And then also we'll have a booth at Intersolar in San Diego. And that's the end of February. So I believe we have some time for questions, but just in case I don't answer your specific question, please feel free to shoot me an email. And again, thank you for joining us.
All right. Thank you so much, Karen. It's now time to move into our Q&A session. As a reminder, if you have not already done so, you can ask questions by submitting them into the Q&A box. We do already have some great questions here to get started with. So our first question: what are the issues with solar simulator systems that do not image the illumination field?
Okay. So I touched on it briefly, but without an imaged field, you can have severe fall off in uniformity as you move off the nominal working distance. So as if your sample changes height, or if you're going to go to a different depth of sample height, any height variation ruins uniformity. Also, wavelength uniformity is poor, and calibration is much harder and less stable. So the imaging system, like what we use in our LumiSuns, gives you depth of focus, basically, and so more tolerance on sample positioning.
Next question. Is there a trade-off between uniformity and spectral accuracy when adjusting LED intensities?
Well, so not in imaging systems like the LumiSuns, because the uniformity is determined by the imaging optics, not by the LED intensity ratios, but that is something to look for in other systems. So the imaging systems enable true wavelength tunability without compromising accuracy. I'd say that, I think that answers that one.
Thank you. What do you mean when you say uniformity is less than 0.8% for each individual wavelength?
Okay. Actually, we're less than 0.75%, but I rounded it. This is an excellent question, so thank you to whomever asked this. This distinguishes the IOI LumiSuns, provides better measurement accuracy to the user. And what it means is that any single wavelength fills the field uniformly. This is important to advanced PV researchers using selective spectral illumination, for example, the blue only or the red only that I showed in the graph there, when you can dial it in on the GUI, or infrared only. Most solar simulators only specify uniformity for the combined broadband output. In addition, we calibrate uniformity wavelength by wavelength, not just with the full spectrum. So even with the full spectrum on, uniformity is better overall also when every wavelength meets the criteria. It's not easy to do. We take great care in our optical design and layouts of the die and choosing the proper wavelength distribution. For example, how you would use this feature is with tandem devices, or why it matters, for example, to tandem devices. Each subcell responds to different spectral regions. So if those wavelength regions are non-uniform, then the subcells experience different biases across the field. So in essence, you're causing incorrect, or it will cause incorrect current matching, shifts in fill factor, for example, and inaccurate efficiency values. Thanks.
Thank you. Regarding the LumiProbe module, how do you handle stray light?
Okay, so sort of a standard practice is to take a dark scan that allows you to subtract out any noise from the signal. Another option is to have a dark box. We're presently considering designing that now. But they're sort of standard approaches to controlling the stray light. But one thing is with, for example, if you're using any of the LumiSuns, they have a very high brightness and high level. So the noise isn't as important.
We just got another question here. Can your simulator interface with common PV test equipment? So for example, like Keithley's SMUs, PV measurement tools, or Enlatech EQE systems?
So yes, all of the LumiSuns, all of our solar simulators can certainly function with any of those measurement systems. So, many of those systems are not solar specific. So they don't have the same capability as the LumiProbe. In addition, LumiProbe can be used with other solar simulators that are out there as well. The good news about LumiProbe is that it does exceed the IEC standards, and it can track and correct for temperature. Many other systems don't necessarily do that. But because it's designed specifically for solar simulators, it saves time and money for setup, and it gives you more capability. In addition, you can contact us directly for support, specifically for solar. So all in all, yes, you can use your simulator or use our simulators with other test equipment that's out there. But we recommend going with LumiProbe, just easier to pair the two.
Another question here. Can the illumination area be expanded beyond 220 millimeters for custom modules or prototypes?
Okay. So short answer is yes, we're capable of doing that. In fact, we're going to have a 450 by 450 millimeter module. But LumiSuns are mostly offered as off-the-shelf type of illuminators. But it depends on the customer's need. So we tailor the next gen sizes to meet demand. If we have a high demand for a specific size of illumination field, we of course would evolve our LumiSuns to cover that. If you have specific requests, you can always reach out to me. Let me know, and we can discuss the possibilities. But right now, the LumiSuns that we do offer vary from 50 by 50 millimeters square to 220 millimeters by 220 millimeters. The LumiSun high brightness module is a 55 by 55 millimeter area, and that's up to 20 suns. The other lumisuns go from, say, even below zero 0.1 suns all the way up to 1.2 suns in general. And they're all class AAA plus as well. And as I mentioned, with low spectral deviation, that's what you really want to look for in addition to class. So, give me a ring, or send me an email, and we can talk if there's a different type of size illuminator that you really want.
Right, for this next question, apologies in advance if I mispronounce anything. But can the simulator independently bias the top and bottom cells of a perovskite SI tandem to study current matching? Again, apologies.
No, I completely understand. That can be a tough word to pronounce. It's perovskite, and I believe they mean silicon. So yes, I think you did very well. The circumstances. Let's see. So can it independently bias the top and bottom? Okay, of perovskite. Yes, absolutely. So it is in fact a key feature of the lumisuns. We use a multi-channel LED array with individually controllable wavelengths, and that's really key, each with high uniformity and capable of a range anywhere from 0.1 suns all the way up to 1.2 suns. So you can actually go greater than 1 sun. Gives you a little bit of margin in there. You can turn on only the wavelengths absorbed by the top cell, or only those absorbed by the bottom cell, or any combination or both of both. If you remember, one of the slides that I showed was specific to the red and the blue, but you can also turn on red, white, and blue, or you can turn on just green, or perhaps in the infrared, if you want to selectively study behavior, not only of a PV cell, but also if you're looking for certain materials degradation or other application where you want to look at individual wavelengths and not just the whole spectrum. So it's certainly capable of doing that. All of our illuminator systems are capable of individual wavelength control. So yes, so specifically for perovskite and silicon tandem, yes, it can definitely be used for that kind of testing. Let's see. Yeah, that's good.
All right, and I think we have time for one more question here. Is the LumiSun 220 capable of both AM0 and AM 1.5G?
Yes, it is. So that's something you want to look for out in the solar simulator world when you're shopping for one. Those two spectra are necessarily different. AM0 is, of course, space related, right, for satellite testing or anything that has not had the attenuation of the Earth's atmosphere. AM 1.5G is the terrestrial reference spectrum. And the difference between those two is quite significant when you're designing a solar simulator, because AM 0 has both a higher irradiance overall and also none of the absorption dips that you experience in the AM 1.5G reference spectrum, which is the terrestrial version. For all of our lumisuns, well, I shouldn't say all right now, but for most of the lumisuns, we cover the AM0 and the AM 1.5G. So in particular, for the LumiSun 220, yes, that will be a feature of both, in fact. And it is class AAA plus with low spectral deviation. So you'll be able to test a range of samples, both under space conditions or UV testing, perhaps, and also under the Earth's conditions at terrestrial AM 1.5G. So.
Thank you so much for that. That is pretty much all the time we have for today's program. If you were not able to ask your question, or if you have any additional questions, you can email them to isnainfo@divcom.com or contact our sponsor for today's webinar. I do just have a few quick housekeeping notes to go over before we officially close out. If you could please fill out the short evaluation form that will appear on the webinar console, this will help us better serve your needs in future webinars. And as a reminder, The on-demand materials will be emailed to everyone within 2 business days. This will include a PDF of the slides as well as a link to the recording of today's presentation. And thank you again to Karen for an excellent presentation today, and thank you to all of our attendees for taking the time out of your busy days to join us. This webinar was brought to you by Intersolar and Energy Storage North America and sponsored by Innovations in Optics. Thank you all and have a great day.
Thank you, everyone.